Okay, cool. So we are now on to section 12 of L&L's classical mechanics. And this section is titled Determination of the Potential Energy from the Period of Oscillation. Let us consider to what extent the form of potential energy, U of x, of a field in which a particle is oscillating can be deduced from a knowledge of the period of oscillation, which I will denote as tau, as a function of the energy E. Mathematically, this involves the solution of the integral equation of integral from x1 to x2 of dx over square root of E minus U of x, all being multiplied by the square root of 2m. And in which U of x is regarded as unknown and T of E as known. So we do know the period as a function of energy, and now we're trying to see if we can denote U. We shall assume that the required function has only one minimum in the region of space considered, leaving aside the question whether there exist solutions of the integral which do not meet this condition. And for convenience, we take the origin at the position of minimum potential energy and take this minimum energy to be 0. Now, in this integral, we regard the coordinate x as a function of u. The function x of u is two-valued. Each value of the potential energy corresponds to two different values of x. Accordingly, this integral must be divided into two parts before replacing dx by dx du times du. One from x equals x1 to x equals 0, and the other from x equals 0 to x equals x2. We shall rewrite the function x of u in these ranges as x approaches x1 of u and x equals x2 of u, respectively. The limits of integration with respect to u are evidently e and 0, so that we finally have an integral of the form T of e equals square root of 2m times the integral from 0 to e of dx2 of u over du times du over the square root of e minus u, plus the square root of 2m times the integral from e to 0 of dx1 of u over du times du over the square root of e minus u. So essentially we're trying to get our bounds from the function of the period. And this can also be just written as the square root of 2m times the integral from 0 to e of dx2 minus dx1 over du times du over the square root of e minus u. If both sides of this equation are divided by alpha minus e inside of a square root, where alpha is a parameter and integrated with respect to e from 0 to alpha, then we get a result of integral from 0 to alpha of the period as a function of energy dE divided by the square root of alpha minus e is going to be equal to the square root of 2m times the double integral from 0 to a alpha and from 0 to e of, again, dx2 minus dx1 over du times du de over the square root of alpha minus e times the square root of e minus u. Now, this integral, the integral over e, is elementary. Its value is pi. We can see this by, again, our integral for e is going to be actually, let me change the order of integration first so this makes a little more sense. This can also be written as two separate integrals. Integral from 0 to alpha of dx2 minus dx1 over du times du, and the integral from u to alpha of dE over square root of alpha minus e times the square root of e minus u. Now, once I've separated these two integrals, I went from here to here, and the integral on the right is elementary. If I solve this integral on its own, it would be the integral from u to alpha of dE over the square root of alpha minus e times the square root of e minus u. Now I can make a substitution here where e is equal to alpha plus u over 2 plus alpha minus u over 2 cosine theta. Now I do this because I want at some point for my integral to be u, or for my value of e to be u, and for my value of e to be alpha. And this is clear because when theta is equal to 0, I would get cosine of 0, which is 1. So alpha plus alpha, both over 2, which would just give me alpha. And I have u over 2 plus a negative u over 2, which would be 0 u over 2. Thus, at this point, my integrand returns, or my values return alpha. And when theta equals pi, I would get cosine of pi, which is negative 1, which gives me alpha minus alpha, which would give me 0, and u plus a negative u times negative 1, so it would be u over 2 plus u over 2, which would just give me a value of u, which is exactly what I want. So my new integral in terms of this is the integral from pi to 0, because I replaced u, or I get the value of u for when theta equals pi, and I get the value of alpha when theta equals 0. And now, since I made this as my substitution for e, my dE would just be negative alpha minus u over 2 sine theta. So I have negative alpha minus u over 2 sine theta, all being divided by, now I need to calculate my divisors. Alpha minus e is just alpha minus alpha plus u over 2 plus alpha minus u over 2 cosine theta. And this returns, if I write this as 2 alpha over 2 minus alpha plus u over 2, this just gives me alpha minus u over 2. So I have alpha minus u over 2, and if I distribute the negative sign, minus alpha minus u over 2 cosine theta, I would get alpha minus u over 2 times 1 minus cosine theta. So that would be my first value. Alpha minus u over 2, 1 minus cosine theta. And if I solve for e minus u equals alpha plus u over 2 plus alpha minus u over 2 cosine theta minus u, I can do the same thing. So I write it as alpha plus u over 2 minus 2u over 2, which just returns a value of alpha minus u over 2. And then I have alpha minus u over 2 plus alpha minus u over 2 cosine theta, which can just be factored as alpha minus u over 2, 1 plus cosine theta. So I get alpha minus u over 2 times 1 plus cosine theta. Now expanding this term, 1 plus cosine theta, 1 minus cosine theta, gives me a value of 1 minus cosine squared theta. And I can just square my factor out in the front. So 1 minus cosine squared theta. And all of this is again inside of a square root. So here we see some nice cancellation happening. We have alpha minus u over 2 squared. The squared cancels with the square root, and it gets canceled by this term as well. And 1 minus cosine squared theta is just sine squared theta. And now we have this negative out front. So our final remaining integral is the integral from pi to 0 of negative 1 d theta. And I forgot to write my d theta over here. And this is symmetric, so I can just say it's the integral from 0 to pi of 1 d theta, which just returns me a value of pi. And that is how this integral is elementary. And that actually makes the second integral we have trivial. So the final result for this whole double integrand expression here, because this returns me a value of pi, so now I just have to work on this, which this is trivial. And it gets me the integral from 0 to alpha of the period as a function of energy divided by the square root of alpha minus e is just equal to pi times the square root of 2m times x2 of alpha minus x1 of alpha. And since x2 of 0 is equal to x1 of 0 from our boundary conditions and initial conditions, we write u in place of a to obtain a final result of x2 of u minus x1 of u equals 1 over pi square root of 2m times the integral from 0 to u of the period as a function of energy dE divided by the square root of u minus e. Thus, the known functions, the period as a function of energy, can be used to determine the difference x2 of u minus x1 of u, and the functions x2 and x1 themselves may remain indeterminate. This means that there are not one, but an infinity of curves where u equals u of x, which give the prescribed dependence of period on energy, and differ in such a way that the difference between the two values of x corresponding to each value of u is the same for every curve. This indeterminacy of the solution can be removed if we impose the condition that the curve u equals u of x must be symmetrical about the u-axis. That is, if x2 is equal to negative x1, which can just be defined as x. So if x2 of u equals negative x1 of u. We can just define this as x of u. And in this case, this formula gives the unique expression of x of u equals 1 over 2 pi square root of 2m times the integral from 0 to u of the period as a function of energy, dE, all divided by the square root of u minus e. And this is pretty much a special case for when we can find the potential energy as a function of the period. And in general, you will have an infinite amount of curves, but with specific substitutions, you will be able to get specific values for this integral.